Part 1. Please find a quiet place to sit or lie and to listen to this audio. Once seated or lying, close your eyes. Focus your attention on your breath. When you are ready, inhale slowly. Let the air fill your lungs. And then exhale slowly. Let the air escape from your lungs. Inhale again. And then exhale again. Notice how your stomach rises as you inhale and falls as you exhale. Rises as you inhale and falls as you exhale. If your mind wanders, don't be concerned. Just gradually shift your attention back to my voice. Part 2. I will soon ask you to hold your breath as long as you can. That is, on the count of 3, inhale and hold your breath. 1, 2, 3. After a minute or so, you might feel the urge to breathe. But if you can, don't respond to this urge. Instead, merely observe this urge. Observe the thoughts that penetrate your awareness. Just watch the discomfort from afar, as if an impartial observer. For example, clarify where in your body you feel this urge. Observe your thoughts as if watching a movie with subtitles. Be attuned to thoughts that attempt to mislead you, thoughts like, I need to breathe now, or this exercise is silly. Thank your mind for these thoughts, but recognize that you don't need to be guided by these thoughts. Perhaps also observe other sensations and feelings in your body. Perceive every pang in your chest or urge to breathe as an opportunity to experience a unique sensation, to experience something novel. Persist as long as you can. But then eventually, when you're ready, you can breathe normally again. Notice the feeling of relaxation that now permeates your body. Experience the serenity that now infuses your mind. Part 3. Now with your eyes still shut, name as many objects in the room as you can. You might refer to the chair on which you were seated, a rug that covers the cold wooden floor below, a print on the wall, a pot plant with wilted leaves in the corner, or an air conditioner behind you, humming gently. How do you know the room contains these objects? Well, of course, you saw these objects before you closed your eyes. But how did your brain determine which objects are in the room? For example, how does the light, reflecting from the chair, enter your eyes and then travel to your brain? And then how does the brain recognize the object is a chair instead of a ham sandwich or a rug instead of a stingray? We will now trace the journey of these rays of light. We will imagine how rays of light emanate from a chair to your brain. Part 4. Keep your eyes closed, but pretend your eyes are open. Pretend the rays of light in the room can penetrate your eyelids and travel to the brain. Now imagine a specific ray of light emanating from an object in the room, such as a chair. Actually, light tends to travel very quickly, quicker than anything else, but imagine for now that light travels slowly. Imagine you can watch the light travelling as slow as a tortoise from the object to your eye. If your eyes were open, the light would strike the outer layer or casing of your eye, the cornea. The light would then bend slightly. For example, light that strikes the cornea near the top of your eye bends downward slightly. Light that strikes the cornea near the bottom of your eye bends upward slightly. About 1/3 of the way into the eye, most of this light is then absorbed by 2 layers of coloured cells. In some people, these cells are brown. In a few people, these cells seem light blue or green. These cells, when combined, look like a sparking donut and are called the iris, and these cells determine the colour of your eyes. The hole at the centre of this donut is black. This hole is called the pupil. Rays of light penetrate only this pupil. Focus your attention on a ray of light that has emanated from a chair or object, bent after striking your cornea, and has now penetrated or passed the pupil or hole of the donut. About halfway into the eye, the light that has penetrated the pupil now strikes another structure called the lens. Sometimes this structure is like a spherical marble, and at other times this structure is stretched from above and below and looks thinner. Imagine for a moment this marble being stretched into a thin marble and then released to form a thicker marble. Stretch and then release. Stretch and then release. The ray of light upon striking this marble or lens now bends even more. If the lens is stretched, the light does not bend much. If the lens is not stretched but more spherical, the light bends more. At this stage, don't worry about why the lens bends light. You don't need to know the purpose of this lens, a structure that actually focuses light on the retina at the back. You don't need to know the lens stretches or releases depending on whether your eyes are focused on distant objects or nearby objects. But just imagine the light bend after striking the lens. Part 5. Eventually, the light will strike the back of your eye, called the retina. Now focus your attention on the back of your eye. Imagine you can observe the back of your eye as though piercing through a special microscope. You soon realise the back of your eye, or retina, does not merely comprise one layer of cells. Instead, the back of your eye comprises several distinct layers. The back layer, farthest away from the cornea, are called photoreceptors. The next layer, the second farthest from the cornea, comprise bipolar cells and horizontal cells, both of which will be defined later. The final layer, the layer closest to the front of your eyes, contains amacrine cells and ganglion cells. Don't worry if you can't memorise these layers now. And also don't worry if these terms like horizontal cells or amacrine cells seem a bit unfamiliar or even overwhelming. Just focus your attention on the observation that retinas at the back of your eye comprise several distinct layers. Part 6. Now shift your attention to the rays of light that have emanated from an object in the room, such as a chair, and penetrated your cornea and pupil to each retina. As you imagine or observe this ray of light approaching the retina, an unexpected event unfolds. Perhaps you'd expected the ray of light to bounce or spring backwards after reaching the retina. Or perhaps you expected the ray of light to gradually become absorbed in the various layers of the retina. But the ray of light does not behave quite as you anticipated. Instead, the ray of light simply passes through the layers, as if these layers were invisible. But then eventually, the ray of light strikes the final layer of cells in the retina, the layer that is farthest from the cornea, called the photoreceptors. Now zoom your attention towards this layer of photoreceptors. You then notice that not all the photoreceptors are the same. Towards the centre of this layer, sometimes called the fovea, most of the cells resemble small cones. Farther from the centre, such as near the top or bottom of the retina, most of the cells resemble small rods or cylinders. Now the cones are obviously called cones, and the rods are obviously called the rods. So what happens when the light strikes these rods and cones? What happens to the light? What happens to the rods and cones? In essence, the light seems to be absorbed by the rods and cones. And then, as soon as these rods and cones absorb light, their level of activity increases. Imagine that as soon as they absorb light, these rods and cones begin to generate action potentials, like sparks of energy. Now later we will actually modify this story, but for the moment, simply imagine that rays of light vanish into the rods and cones, and the rods and cones produce sparks of energy or action potentials. Part 7. But what changes do these flashes of energy or action potentials generate? In essence, after they absorb light, these rods and cones activate two categories of cells in the next layer of the retina. The layer slightly closer to the front of your eye, called bipolar cells and horizontal cells. And these bipolar and horizontal cells activate two clusters of cells in the final layer of the retina, the layer actually closest to the front of your eye, including amacrine cells and ganglion cells. And the axons that emanate from these ganglion cells then actually travel to the brain. Now, this sequence of action potentials is very complex. Don't worry about this complexity now. Just appreciate that after the rods and cones are activated, two more layers of cells are activated in turn, and the final layer, closest to the cornea, sends action potentials to the brain. But why does the retina comprise these distinct categories of cells, such as bipolar cells, horizontal cells, amacrine cells, and ganglion cells? Surely the rods and cones should send information to the brain themselves. Well, actually, each category of cells offers some key benefits. To illustrate, imagine that you are sitting in a dark room but exposed to very faint light in the periphery. This faint light will activate many rods, but only to a minimal extent. You can visualize each rod located on the edge of your retina, sending action potentials or sparks of energy, but only occasionally. However, many of these rods send these action potentials or sparks of energy to the same bipolar cell. Consequently, this bipolar cell will be activated to a strong extent. Because of this arrangement, bipolar cells can be sensitive to very faint light. We can thus see, at least to some extent, even in quite a dark room. Part 8. During this description, you imagine that light activates the rods and cones, and these rods and cones then activate other cells, such as bipolar cells. Technically, however, this description is not quite correct. In practice, when exposed to light, rods and cones don't actually generate more action potentials and sparks of energy. Actually, when exposed to light, rods and cones generate fewer action potentials or sparks of energy than usual. And furthermore, these rods and cones don't actually activate bipolar cells. Instead, these rods and cones actually inhibit bipolar cells when activated. Therefore, in response to light, rods and cones don't inhibit bipolar cells as effectively as usual. Consequently, light does ultimately activate bipolar cells, as you assumed before, but the sequence of events is perhaps more complex than you'd imagined. Don't worry if you don't understand these details. Just appreciate that light does activate bipolar cells, and these bipolar cells do activate ganglion cells, but perhaps appreciate the sequence of events is actually quite complex. Part 9. The ganglion cells at the front of your retina then send action potentials to the brain. For a moment, imagine cells at the front of your retina with axons resembling hoses that reach the brain. Don't worry if this image is hazy. As you maintain this image, repeat to yourself the term ganglion cells, ganglion cells, ganglion cells. However, the route from the retina to the brain is not straightforward. To clarify this route, attempt to visualize three main layers of your retina: the rods and cones at the back, the bipolar and horizontal cells in the middle, and ganglion cells in the front. Then visualize axons emanating from the ganglion cells. These axons converge in front of this layer of cells to form a single bundle. Then, if you can, imagine this single bundle of axons suddenly twisting towards the back of your head, burrowing through the other layers in your retina, and drilling through the back of your eye. The other layers, the rods, the cones, the bipolar cells, and horizontal cells, thus surround this bundle of axons. And at this point in your retina, there are no rods and cones. In essence, the eye cannot see at this point. The bundle of axons emanating from the ganglion cells is called the optic nerve. And as you visualize this bundle of axons penetrating the back of your eye, repeat the term optic nerve, optic nerve, optic nerve. Now imagine this optic nerve travelling towards the brain. In particular, this optic nerve, this bundle of axons, meanders along the lower surface of your cortex, sort of the top half of your brain. After about, say, 4 centimetres, the optic nerve from each eye converges to one point in the middle called the optic chiasm. Some of the axons from one side cross to the other side of the brain, whereas other axons do not cross. Now, which axons cross is not actually random. In particular, axons that responded to light from the left side of your body cross to the right side of your brain. Axons that responded to light from the right side of your body cross to the left side of your brain. Don't worry if this principle is hard to understand. Just note that axons don't cross randomly. And these axons continue to travel a few centimetres further, eventually reaching a region called the lateral genicular nucleus, a part of the thalamus. The region is about, say, 6 centimetres from the front of your head and resembles a small knees. Actually, geniculate is derived from the Latin word genu, meaning knee. Therefore, try to visualise a tiny knee on each side of the brain while repeating the term lateral geniculate nucleus. Lateral geniculate nucleus. Lateral geniculate nucleus. Admittedly, not all these cells from the retina, these ganglion cells, travel to this lateral geniculate nucleus. For example, some cells travel to a region just above the midbrain called the superior colliculus. A few cells travel to parts of the hypothalamus to influence when we feel sleepy or awake. But most of these ganglion cells travel to the lateral geniculate nucleus. Finally, axons from the lateral geniculate nucleus travel to the primary visual cortex towards the back of your head. The primary visual cortex determines which features or objects seem to appear in the environment. That is, the primary visual cortex is the first location at which we become aware of what we see.